Hello everyone. I'd like to talk about a really neat application layer protocol that's used to convert from human readable names like google.com into IP addresses. And this is an IP address I grabbed from google.com a moment ago. And this protocol is known as the domain name system, or DNS for short. And we're going to talk about how you send a message to a DNS server like, tell me what's google.com, and then what a DNS server would send you back. Like, okay, one of the IP addresses is this. So I'll explain how to do that. First, I'm going to show just a basic recursive DNS query. And then I will explain what an iterative DNS query is. And I will show both of these happening in the terminal and in Wireshark. Okay, so here I am in Wireshark, and let me click on my Ethernet device, which is where I'm communicating with the internet. And I'll filter down just to DNS packets here. Now let me pop over to the terminal. I'm going to type dig at 8.8.8.8 google.com. Now I see a couple things happen in the background, so let me stop this. Looking in the terminal, I can see that I got an answer here. So my question was, what's the IP address of google.com? And my answer is this. 142.250.64.110. Now what's this 8.8.8.8? Well, if I look at Wireshark, I can see that's my destination. I'm sending a UDP packet, which encapsulates a request. I'm asking what is called the A name record of google.com. So I'm asking for an IP address of google.com. And I'm sending that to 8.8.8.8. Well, that is a DNS server that Google has been running for many years. And so that's the destination where I need to send this UDP packet. And by the way, just to note, this uses UDP instead of TCP because the UDP header is much more compact. And we need this, this happens very often that we ask for domain names. So we're trying to keep everything as compact as possible. We don't need a three-way handshake and all that stuff. So sometimes these packets will get dropped, but then you just ask again. Okay, so this is a UDP protocol. Now I want to dig a little bit more into the binary format of these messages. And so I have open here the RFC, the document that talks about what is the format of this protocol. And it's a binary protocol, which I've talked about before. So these are not human readable messages, but they have a very specific byte layout with information in it. So every DNS message, the payload, so after I get through the link layer, IP layer, and transport layer, the payload is what this document is going to describe here. And so I see it starts off with a header, which has information about what's to follow in this message. And so yeah, let's look at the header first, actually. So the header consists of 12 bytes. You can see each of these rows is 2 bytes, and there are 6 of them. The first row here is what's called the transaction ID. If I look at that, okay, so here is, the header, as I said, is the first 12 bytes, the first 2 of which are the transaction ID. So in hex, my transaction ID here was DDOB. And the way that I can tell that this second message here is actually a response to my first DNS message is that I have the same transaction ID, okay? So this is a way for me to keep track of, oh, this is a response to that particular query that I just made with that transaction ID. Okay, after that, we pack a whole bunch of variables into 2 bytes. And I'm just going to focus on 2 of them for now. So the first one is QR. And luckily, Wireshark parses these for us. In a homework, I'll have you parse some of these by yourself. But Wireshark does it for us. So it says, okay, this QR, it's supposed to be 0 if I was making a request or 1 if I was getting a response. And I look at this and I say, okay, yep, that is 0 for my first message. And then I get a response and it's a 1. Okay, so both the request and the response have the same format. So QR is 0 for the request, QR is 1 for the response. I also want to look at this bit here, which is RR. If we look, or sorry, RD. recursion desired. And so what I was asking for here was what's called a recursive DNS query. And this is definitely easiest to explain with a picture here. So let's say that this is my device here, and I make a request to Google's DNS server 8.8.8.8, and I'm asking for recursion. So let me draw a little arrow there that shows my request going out. And so what Google is going to do is send my DNS request to what's known as a root DNS server. So this is a root level DNS server. And so, as you can imagine, there are a lot of domain names out there on the internet, and they exist in a hierarchy. The root level DNS server is only actually responsible for keeping track of what to do with what are called the top level domain DNS servers. All right, so we have some top level domain servers for .com addresses. We've got some top level domain name servers for .edu, .org, etc. So these are called the top level domain DNS servers, or TLD. And there's tons of these actually, just like there are tons of root level DNS servers as well. So there's a bunch of DNS servers with .com. We'll see that in a second. But yeah, so for now, suffice it to say that Google bounces this up to a root level, which finds the appropriate top level domain. In our example here, that'd be .com. And then what the top level domain is going to do is it's going to find what's called the authoritative server that knows a little bit more about Google, for example. So this branches out into a bunch of different authoritative servers. The one we're looking for is Google. And this authoritative server will know all sorts of stuff. Not just what's google.com, but also maybe what's images.google.com, what's the mail server for google.com, things like that. So this will bounce us down to what's known as the authoritative server. So we're getting more and more specific here. We start at the root of a DNS tree here, and then we end up down at the authoritative server, which hopefully has the answer that we're looking for. And if it does, what it'll do is it'll just send that right back to the .com here. And then the .com will send that information back to the root level. And then the root level will send that information back to the DNS server that made the request in the first place. All right, so it comes back here, and then finally it sends it back to me. But as far as I'm concerned, I made one request and got one response, although there was a lot going on behind the scenes here. Okay. As far as I can see in Wireshark, there was one request and there was one response, but that's because I desired recursion, and this DNS server that I connected to is actually capable of executing recursive responses. All right. So that's what that's all about. Now let's just look a little bit more about the format of the question that I asked. So I have to tell how many questions I'm asking. In this case, I'm just asking one. Okay. There are other things I can get back. I'll talk about them in a moment, but let me just focus on the questions. So if I scroll down, I see that the format of a question starts off with a name, and then it has something called QType, which is what kind of a record I'm asking for, and then QClass, which for our purposes right now it's going to be IN or internet. Okay, but I want to focus a little more on the type right now. So I jumped up to section 322 in this RFC, and I see all these different types. And apparently, if I look at Wireshark, the one that I made is an A-type record. And that says a host address. Okay, great. Yeah, I was asking for an IP address. So let's go back down and let's see if we can match the binary. So apparently an A request is a 1. So let's see if we can find that. First, we have to get through the name. So this is a sequence of labels where each label consists of a length octet followed by that number of octets. So what does that mean? Okay, actually easier to explain just by looking at an example here. If I jump to the query, so this is the beginning of the question, so I've gotten through the header. and this is my question. If I look at the first byte here, it's a 6. And that says, okay, I need you to go 6 characters. So this is 6F, 6F. And actually, it'd probably be helpful if I pop back into the terminal real quick and show you an ASCII cable, so you can see what we're looking at here. So first byte here was 6, and that says, okay, the first part of the URL that I'm trying to resolve here has 6 characters. Okay, so hex 67, what's that? Hex 67 is a G. Okay, good. G for Google, right? Then we see hex 6F, and hex 6F is an O, and I see 2 of those. Okay, so anyway, hopefully now you're convinced that what we're seeing here is 6 characters, GOOGLE, and then we have the .com part. And so it doesn't put the dot in there. What it does instead is say, okay, I knew this was going to be 6 characters, so after this I'm expecting something else possibly. And it says, okay, the next thing that I'm looking at is 3 characters. Okay, so that's going to be the .com part. So that would be COM. And then I go to the next byte and I see 0. And that means I'm done reading the string because, well, there's no more components, or in other words, there's a component of length 0. So I can move on. All right, so that's why when I highlight the name here, it shows me those bytes, okay? Now, what about the A? Okay, so that's what comes right next. It's 2 bytes describing the type, and there we see it, right? The A name, I told you that was going to be a 1. And then finally we have our class internet, which is 1. Okay. Let's see, what else we got here? So additional records. Okay, we don't need to worry about this right now. All right, so let me jump into the response here and have a look at what got sent back. And a couple interesting things are going to happen here. So we actually, as I showed you, now it says it's a response, and it says a couple other things. It tells me that recursion is available. That's another thing that we can see in the header. So hey, I wanted a recursive response, and this server was capable of doing it, so I'm in luck. That's great. Now I see there's actually a couple other things. So before I just had one question, right? And an additional record. This time I have a question and I have an answer. Okay, so the answer is what holds the information that I'm looking for. If I go back up and look at the overall format of this, it's header followed by the questions, followed by the answers, and then authority records and additional records. So what's interesting is it actually repeats the response, repeats the question that I asked. So once I get through the header, I actually have the same bytes, if you look at it, the same exact bytes as I had in the request, in the response. You see that? Back and forth there. Okay, but now I have these answers, and I can tell how many answers I have by looking at the header, right? Because the header tells me this AN count here, and that's 1. Okay, so I got 1 answer. That's the AN count. So once I get through the questions, let me jump through the answer, and let me look at this. And now when I highlight google.com, you see it's only 2 bytes. But that seems a little strange, right? Google and com are definitely more than 2 bytes, especially if I have to also say what the length of each one of those is. So this is using a compressed format of representing the names here. And so to show you what this actually all means, let me jump into Python and just get this whole byte stream here. So let me highlight this and I'll say copy as hex stream. And if I jump into Python and I say, okay, you know, I'll say my maybe response is equal to bytes.from hex. I'll put this string here. Now I've turned this into a byte array. And as I told you, the header was the first 12 bytes. So I'll slice that out. I'm not really worried about that right now. And then let's see. So the question ended up being. Whoops. Let me get to the question here. The question ended up being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 bytes. Okay. So 16 bytes. So the question would be, I would slice out from index 12 to index 12 plus 16. All right, and now I'm looking at this, and just make sure I'm aligned properly. I see that the first 2 bytes of answer are C0 and 0C. So let's have a look at that. So if I were to look at my result starting at 12 plus 16 and going up to 2 bytes after that, I see C0 and 0C. Okay, so what does that mean? C0, if I look back at the RFC and I scroll down a little bit, it tells me something about message compression. And it says, okay, usually when I get to the name section, I'm looking for the length of what's the next thing to follow. So before, when I was looking at google.com in this question, then I was expecting that, the first byte would tell me, okay, how long is the first part of it? So 6, Google is six characters. But here, I see something different. I see C0. And what C0 is this byte here. So C0 is 11000000. So this is 1 byte, and it's telling me that the first 2 bits are 1 and the rest are 0. And what that means is it's an offset. Okay, so I'm not actually expecting a character after this. What I'm expecting is basically a pointer. Okay? So I look at this C0 and then I see 0C. Okay. Well, 0C is 12. What that tells me is, okay, the name that you're looking for is actually 12 bytes into the overall DNS response here. And actually, that's exactly what we saw, right? So what's happening here is it's repeating in the answer. It's saying, hey, I'm not going to bother putting out ctraily.com again. Or, sorry, google.com again. I'm not going to bother writing that again. I'm just going to give a pointer that says, hey, C0. Okay, that means pointer. 0C says, go to 12 bytes into the message. We saw 12 bytes into the message was exactly where this name is. Okay, so it doesn't have to repeat that name, and it can be much more compressed. So that's the way the compressed format works. And if just to look back at the RFC real quick, it says, okay, look, when you're looking at this first byte, you're either in a sequence of labels, like I showed at the beginning, where you say, okay, 6 bytes, there they are. Now 3 bytes, there they are, and so on and so forth. Or you're a pointer, or you can actually start with a sequence and end with a pointer. So maybe I was asking for images.google.com, but I already had google.com up there somewhere. I could have coded images first and then get a pointer to google.com. We'll see some examples of that as we move forward. Good. So hopefully the compression scheme makes sense. So this is saying, hey, all right, once I've gotten through the queries, the answer is saying it's an answer to google.com. I don't have to repeat the whole thing because it's earlier on in the message. But this is going to follow the same this overall resource record format, actually slightly different format from the questions. So the record comes back, okay, first is the name, only 2 bytes. Next is the type. And once again, we're going to see here that this is an A record. So it says, great, this is an A record. Internet class. Time to live. So these actually, the internet is always changing. And so I could actually change the IP address that my domain name points to. And so these records can get stale, and that's important to know when they get stale. And then finally, so once I get through TTL, I've got the length, RD length. That's the length of the actual information that's associated to this record. And in this case, I was asking for an IP address. This is going to give me back an IPv4 address, which is 4 bytes, and there it is. Okay, so it gave me one answer, and that's it. So hopefully it's making sense a little bit as I dig into the guts of these binary messages. All right, so that was it for the basic recursive DNS query. The reason I said basic here is just because we only have one message and one response. But now I'm going to complicate things a little bit, and I'm going to do more of the work myself of going through this hierarchy of servers. So let me use the same basic setup here, but instead of relying on this intermediate server from Google, I'm going to do something called an iterative query where I basically do this work by myself. And so there's all the same servers out here, but I'm going to communicate with them directly. And so what I'll do is I'll send a request first to a root level server. And the root level server, I'll say I do not want recursion this time. So the root level server is going to respond with information about which top level domain server I should go to. So let's do that. So the root level server will just respond and tell me, okay, here's the top level domain that you need to go to. And then I find out, for example, that maybe it's .com. Okay, so then I'll go to .com and I'll say, which authoritative server do I need to go to? It will respond to me with that information. And then I will visit the authoritative server. And then hopefully the authoritative server actually has the information that I need. And it will respond with that information. And then I can declare victory. So now what I'd like to do is simulate this kind of a request. And so I need to find a root level server to query directly. So it turns out if I just type dig by itself, it'll show me some available root servers. So let me just take the first one on the list here. I'll take the IPv4. By the way, quadruple A is IPv6 record. I'm just going to stick to IPv4 records in this tutorial, but just know that those are available as well. Okay, so here is a root level DNS server that I can ask information of. So let me now say dig, and I'm going to say plus no recurse. I don't want it to do anything recursive. But I'll use this server and I'll make... Now let me ask for ctraily.com, because this is going to turn out to be a little more interesting than google.com. I'll show you why as we go through this. Okay, so let me pop in a Wireshark, restart this capture here, and see what happens with this message. All right, so once again, I sent out a single request, it got a single response. If I look at this request, now I see that recursion desired is 0. Okay? The response that comes back does not have any answers to the query that I made, but it does have some authority records and additional records. The authority records tell me about information, actually the domain names of name servers for the top level domain. So it turns out here, all of these servers are DNS servers that have information about .com domains. So if you were to register a .com domain, you would have to propagate that DNS record to all of these servers. That's what your, hover.com or whatever service that you're using will do when you register a .com. Okay, so I can use one of those .coms, and if I go to the additional records, I can actually see some A name records for those. So I see, okay, here's the A name record for a.gtldservers.net. And so I get an IP address. Okay, 192.5.6.30. So what I just got back from this root level server was an IP address of some top level domain DNS server that I can query. So let me take that now, that 192.5.6.30, and let me query that. All right, so 192.5.6.30. Let's query that with the same exact query. And when I do that, I get a message that is very similar. So once again, I'm not desiring recursion, so the response that I have does not yet have my answer for what I'm looking for, but once again, it does actually have some authority records, and so it's telling me, oh, there's a couple authoritative name servers that you can look at. One of them is ns1.hover.com, the other one is ns2.hover.com, and that is actually, I mentioned Hover because that's the one that I use for ctraily.com. Okay. So let's try to look at one of those, and they should have more information about the IP address of. So these are the authoritative servers. So I look at the IP address of the first one, in the additional records here, it's 216.40.47.26. Okay, so I'm going to clear Wireshark here and make this request. And what we see here is finally we actually get an answer, because if I look at the header of this response, it says that this is an authoritative server. So this actually has an answer of what I'm looking for. And it actually gives me 4 answers, because there are 4 different IPv4 addresses that I can use. So the way I have my website set up, I'll just tell you. So this was using, if we go back, actually, let me just show the other one again real quick. So if I go back to the whoops, if I go back and capture right before this, when I was at the authoritative server, or when I was capturing at the top level domain, what are the authoritative servers? It tells me hover.com. So I have my website registered on hover.com. And so then when I go to hover.com's authoritative servers, I get my answer that I'm looking for. So with hover.com, I had registered these a name records. I actually had to do that. I had to go and say a name and put these IP addresses, because these are the 4 IP addresses that are used. If you go to GitHub, I use GitHub pages. So let's see one of them. 185.199.108.153. Let's see, does that match? Yeah. So that's the last one here in the list. Okay. So yeah, you see the 4 of them, they match. So that's what I had to do. Okay. So I went to my authoritative server. I say, hey, here's what you got to do when people get down to you and ask for where's ctrailer.com. All right. Okay. I want to show you one more example here that's a little more complicated. So I want to ask for www.ursinus.edu, so our college. If I type dig, let me start over again. I'll do some different root domain server. I'll do this one this time. Root DNS server. So let me say dig no recurse using this, and I'll say www.ursinus.edu. And let me make sure I'm capturing here. And so I get those 2 messages. And actually, you know what? I'll just look at the rest in the command line here. I think you probably see the messages well enough. Let me just, I can get all the information I need in the command line. So, okay, so it's telling me, I'll keep capturing here, actually. It's telling me I can use one of these servers for the .com. Or no, this is different. These are the edu servers, right? This is ursinus.edu. So now you see the top level domain are actually the edus. So I picked one of those. Let me repeat the request with edu and see what I get. Okay, so now it's telling me, let's look at the response here. So it's telling me that I have to go to this authoritative server, which is balu.ursinus.edu, which I believe has something to do with beluga whale. So, okay, so if I go in the additional record section, I can get the IP address for that. Or I guess I'm not sure what PO is, but that's another one I could use if I wanted to. Okay, but let me go to the beluga or Balu authoritative server. And now here's what's really interesting that's different. If I look at the response here, it tells me it has an answer, right? But the answer is not an IP address. The answer is not an A record. Wait, you lied to me. I was asking for an A. I wanted an IP address. But instead, what it gave me was something called a CNAME, or a canonical name. So I'm in here to let you in on a little secret. www.ursinus.edu is not www.ursinus.edu. In fact, it has a canonical name, or CNAME. If I go back up here and I look and I see, okay, CNAME is a 5 type record. So I see C5, it's a CNAME. And the data here is actually 28 bytes because I have this ursinus-prod, which is 12 characters according to this. And then I have the live well and I have the net. So I've actually got a whole URL string here. And what I got to do is, I'm not done. I've actually got to start all over because I found out it's not even a .edu website. It's actually a .net website using live well. I think that's where the beluga came from. So I actually got to go back up to the root server again, right? Because I was drilling down into these EDUs. I eventually got to an authoritative EDU, which told me, oh, actually, your canonical name is a .net. So I got to go back up to the root server and find a .net. So, okay, fine. I'll go to the root server, and now my request has changed. I'm going to ask for this ursinusprod.livewhale.net. So let me go back up to the root, and I'll ask for this instead. Okay, so we got to start over. So now it's giving us one of these top-level domains for the .net. And again, yeah, I might as well just stick to the terminal for now. So okay, so let me just pick one of them at random, and I'll make my request on that. So I'm at the top-level domain server, I'm asking for this now. Okay, it says here's where you find the authoritative servers for LiveWhale. Actually, they've all got these different names, but apparently they all have this, or I only have an IP address for this one. Okay, fine. So it gave me an A record for one of these authoritative DNS servers, so let me check on that. And then finally, let's see. Finally, I think I have my answer. Yes, I do. Okay, because, yes, it gave me A records back in the answer section. So these are IP addresses that you can use for www.ursinus.edu. It turns out if you ask for a web page on one of these addresses, so actually let me show you real quick. If I were to go into Telnet real quick and say Telnet, this IP address, port 80. Oops, sorry, I meant to say space 80. And if I were to say get /http/1.0, and then I said www, or let's see, host www.ursinus.edu, and then I do this. It says, okay, it looks like I ended up at the right place, but it says moved permanently. So that's kind of interesting. So this www.ursinus.edu is not really what Ursinus' website is. Actually, let's see. Yep. So my browser is going to do a little bit more work on that and eventually find the right place to go. But this is where it'll end up if you do a DNS query. And just to show you, okay, so it gave me that IP address. Just to show you that I wasn't wrong with this. If I say, just let me start where I started off in the beginning. If I do a recursive request on 8.8.8.8 for www.ursinus.edu, I get the same IP addresses that I just got a moment ago with that recursive query. And it also it tells me the CNAME record. So when I do a recursive query with Google Server, it actually also sends me back, hey, I found your A names, but guess what? In the process, I found out that there was a canonical name. So it actually sends me back 5 records. Whereas when I was doing the iterative query, I only got back 4 records because I already figured out myself that the canonical name was this. Okay? So just to review what happened. I was looking for www.ursinus.edu. And so that bounced me to a .edu. I guess I should draw the arrows a little bit differently. But that bounced me to a .edu, which gave me information about, an authoritative name server for Sinus. But then the authoritative name server said, hey, you know what? This website is not actually ursinus.edu. It's Ursinus prod, I guess Ursinus production website, .livewhale.net. Okay? So then I got to start over at the top with Ursinus prod.livewhale.net. And I got to do this whole process over again. So the root level says, okay, here's a .NET server that you can use. So I go to the .NET server. The .NET server tells me, okay, here's the authoritative server for Sinus. I go to that. And then finally I get the IP addresses. That's the idea here. Okay, so I think that's like most of what you're going to run into on the homework. And hopefully you feel very satisfied by knowing this is how we can actually get to ursinus.edu. This is going to get us a lot further into answering that notorious interview question in software engineering interviews of what happens when you go to google.com in your web browser. So in the first 2 homeworks, we did all this stuff with the HTTP protocol. And now we're actually digging into DNS. So maybe the last thing I'll say here is this is actually what's going on in the background when you use getAddressInfo. So if I were to say sock equals socket.socket, I'll say socket.af inet, socket.sock dgram, we'll say just for now. When I say, okay, so I started my Wireshark over here. If I say sock.connect, www.ctrailer.com. Now this may already be cached. I have to see if this is actually going to do anything here. Oh, whoops, I need a port too. Okay, so let me say port 80. Let's see, yes, we did. Okay, so what's happening in the background here is the socket is calling getaddressinfo. And guess what? Getaddressinfo is doing exactly what I just showed you manually. Getaddressinfo is doing all these DNS requests, and that's why you saw this DNS request pop up here. Apparently getaddressinfo asked for a recursive one. Actually, which DNS server did it use? Oh, this is interesting. So it used, there's a DNS server on my router here at home. So my router is like caching DNS requests. And my router can operate as a recursive DNS server. Okay, so yeah, this is my router's IP address. 192.168.50.1. So obviously I'm behind a NAT. Okay, networks. So you can't, you won't know how to connect to me just by knowing this information. That's my router. Many people's routers have that IP address because this is my internal network. Okay, but anyway, so hopefully I was able to demystify some of what happens with getaddressinfo, and you understand how DNS works. I hope you enjoy that.